Hey everybody, gonna start streaming. 1, 2, 3, 4. 1, 2, 3, 4. All right, you can hear me. I can hear you. Let's get this done. Gotta do these midterms. Okay, so we're gonna do both midterms as quickly as I can. If you're online, you can ask a question, but I don't know if anybody's gonna be online because it's not scheduled because I've been pretty busy with other stuff. Okay, so let's do it ASAP. By one's principle, does a parachute work? Does circle all that are true? The easiest way to do these circle all that are true questions is just to go on the side here and mark what's true and false. Opening the parachute decreases the force of gravity on the object. That's false. The object force is always true. The force is always the same. Opening a parachute increases the drag force. That's definitely true. Opening a parachute increases the terminal velocity. It decreases the terminal velocity. Having a parachute will always cause upward acceleration on the object. No, this one is not true. Let me explain why. If you are traveling slower, so 3 different possibilities, let's say. Okay, so if you're traveling slower than the terminal velocity, if you're traveling at the terminal velocity, or if you're traveling faster than the terminal velocity. The way it works when you're jumping out of an airplane is you usually open the parachute in this particular situation. Okay? But there's going to be 2 forces on you in all 3 cases. There's going to be a gravity force, and that's always going to be the same strength. And then there's going to be a drag force pushing up. So if your speed is faster than the terminal velocity, the drag force is going to be bigger than your weight. And so your acceleration vector is going to be pointed up because this force is stronger. In this case, though, here, where the terminal velocity is equal to, that's a specific... Oh, hey, I already drew this Freebody diagram. The drag force is equal to the weight, equal and opposite to the weight in terms of strength, and so the acceleration is going to be 0, and you'll be moving at your terminal velocity. But if you're slower than the terminal velocity, your drag force depends on your speed, right? Relative to the air. So if you're traveling slower, then the drag force is going to be smaller than gravity. And your acceleration vector is going to be pointing down. So in this case, you'll be moving at a constant velocity. In this case, you'll slow down. Your velocity's downwards, so to slow down, your acceleration has to be upwards. In this case, you're moving downwards, but gravity's still winning right now because the drag force isn't strong enough. So your velocity's downward, and your acceleration will be downwards too. And that's why this one is wrong. So I guess this one's the only one that's correct. Person in an International Space Station is described as being weightless. Stuff floats around the room instead of being pulled to the ground. Does the person in orbit around the Earth feel the force of gravity? Yes. They must feel acceleration to go in a circle, but there's no other force but gravity affecting them. Or no, because they're very far from the Earth, force of gravity is 0. Which of these is correct? This is actually a fun question because people often think that this is the answer. They can't both be true, right? But the truth of the matter is you are going in a circle. And to go in a circle, there has to be a net force. So there has to be a force pointing down towards the middle of the Earth in the direction of your acceleration, regardless of where you are on the circle. And so because there has to be an acceleration, there has to be a net force, and that net force is gravity. So yes, the answer is yes. No. Compact disk is spinning at frequency 500 revolutions per minute. We want to find its angular velocity. So it's 500. The trick to these is just to write out revolutions per minute, and then do a unit change to change these into not revolutions in terms of radians per second. So so I'm going to make this revolutions go away. I can describe it in radians instead. 2 pi radians is equal to 1 revolution. Note that all of these are the same. 1 revolution is equal to 2 pi radians. And so that whole thing has value 1. All it does is it converts the units. Similarly, we want the base to be seconds. 1 minute is 60 seconds. And so the result here is 500 times 2 times pi divided by 60. So that's 52.3 rad per second. You don't have to write radians per second. You can write 1 over s, because radians are technically unitless. So you shouldn't be, technically speaking, you shouldn't be writing them. I'm going to write them, though, for clarity. And if you have the word radian in there, you won't lose any marks. If you write this instead, you won't lose any marks either. So either or. This one's technically correct. This one here. But I'll accept this one, just for the sake of clarity. If I turn off the compact disc player, the system slows down until the disk stops spinning. If the slowing down requires delta t is 0.8 seconds, what's the angular acceleration? So we're talking about constant angular acceleration. So omega final is equal to omega initial plus alpha delta t. I'm going to slow down to a stop, so my final angular velocity is 0. My initial angular velocity is 52.3. I don't know what alpha is, but delta t is 0.8. So I solve those algebraically. 52.3 divided by 0.8 is minus 65.4 radians per second squared. Or alternatively, 1 over s squared. Either or. Write the equation for the motion of the angular position of a point on the disk that starts at theta is equal to 0. That's in the initial. At a time when I press the off button. So t is equal to 0 is when I press the off button. So the angular position is going to be the initial angular position plus the initial angular velocity plus alpha over 2t squared. Oh, I forgot to write a t here. So theta is equal to 0 plus 52.3 minus 65.4 divided by 2 times t squared, and I forgot to write a t there. Okay, how many rotations does it undergo? This is an interesting bit because we're not asking for what the final angle is, but that's part of the question. So how long did it take to slow down to a stop? It takes t final is 0.8 seconds. So if you start at 0, you can use this formula to find your final angular position of the speck. So let me do that. 52.3 times 0.8 minus 65.4 times 0.8 times 0.8 divided by 2. That's 20.9. That's 20.9 radians. I'm asking for rotations. So I'm going to divide this answer by the number, so radians, multiply it by, I want rotations, radians. 1 rotation is 2 pi. So I'm going to divide this by 2 pi, which makes sense in its own right. 20.9 divided by 2 times pi. 3.33 times around. Carnival worker is working on a merry-go-round which has a position of 20 seconds. Period of 20 seconds. She stands at the first position at 2 meters, and then she stands 4 meters from the center. What's the angular velocity at the 2 locations? Okay, so angular velocity is the distance you travel in terms of angle divided by the amount of time it takes to go around, especially if you're moving at a constant angular velocity, as this one seems to. Okay, so I'm going to make a note of this. I'll make a note of it in a second. So essentially what I'm asking you for is what's the angular velocity? We're given information about the period. You go 2 pi distance around in one period, and it takes 20 seconds. So that's 0.314 radians per second at both locations. We want speed. That's in meters per second. Compared to the angular velocity. In both these cases, they have the same angular velocity. And now we want the speed. V is equal to R times omega. So the initial radius was 2 meters. So that's 0.628 meters per second. And the final velocity is, then you're at 4 meters. So that's 1.256 meters per second. At which location is her acceleration larger? So she's going in a circle. Velocity is like that over here, and her velocity is like that over here. She has a different speed at both places. V squared over R. Alternatively, we can write this in terms of the angular velocity. Omega R squared over R. So it's omega squared times R. We can calculate this if you want. This acceleration initially and finally. Initially, it's going to be 0.628 all squared divided by 2, and finally it's going to be 1.256 squared divided by 4. 0.628 times 0.628 divided by 2, so 0.197, and finally is 1.256 times 1.256 divided by 4, 0.394. And like we might expect, this one is bigger. And I said we might expect. When you're doing one of these questions, you should always have a sense of what the you should always have a reasonable guess of what the answer might be. It's not just a matter of plugging things into equations. So the idea is both of them have the same angular velocity. So the one with the bigger radius has the bigger acceleration. Okay. So when she's at 4 meters, determine her acceleration and the net force on her. Okay, so her acceleration is pointing towards the middle in this situation. Her acceleration only has an x component, it doesn't have a y component. Whenever we do these, we want to write both components of the vectors because we're going to be using these components to figure out forces. So this is, let's see, it's towards the middle, which is the positive increasing x value. So it's 0.394, and that's 0. And then F net is going to have an x value and a y value, which is going to be equal to the mass times the acceleration. So her mass is 60 kilograms. So it's going to be 60 times 0.394. 23.6 newtons, and that's 0. Now we want to draw the free body diagram. The idea is that we have all the information about the forces, or what the sum of the forces is, and we want to use this to figure out what the different values of the forces are. So the free body diagram, there's a bunch of forces. There's gravity, there's the normal force, and there's a friction force. What kind of friction force is it? It's static friction. Probably points in towards the middle here. How do I know it points towards the middle? I know that the net force has to point towards the middle because of what I know about the acceleration. I definitely know that there's going to be a normal force. I definitely know that there's going to be a weight, but both of those are in the y direction. So there needs to be another force pointing in the x direction. So it's got to be friction. So F friction in the x direction is equal to, well, that. 23.6. You know what? I'm going to do it different. I'm going to do it the way I taught you guys to do it. F friction in the y is equal to 0. Normal force in the x is equal to 0. Normal force in the y is equal to the unknown value. Weight in the x is going to be 0. Weight in the y is going to be 9.81 times 60 minus 588.6. I don't know how big this is, so I'm going to put an F. I'm going to lay everything out this way. You'll note that I started this just by, I wanted to take a shortcut. You can take shortcuts on your test. Here's the thing. A person can always take shortcuts on the test if it means they're going to get the right answer. But if you get the wrong answer for any reason and you took a bunch of shortcuts, you don't get any part marks. Most of you have seen this in the marking of the midterms. If you don't show all the intermediate steps where the marker can figure out what you're doing, the marker's just going to be like, well, they didn't know. So what I'm doing out here for the 100 millionth time is I write out all the components that I do and don't know for the forces. The idea being that I know the direction of these forces, and that's a really helpful thing to know. It's not everything. I don't know how strong they are off the bat, but I label the things I don't know with variables and label the ones I do know, indicating direction. Okay? So now I can put all of these pieces of information together because this term here has to equal that plus that plus that. And this term here has to equal that plus that plus that. Which tells us that the friction force has to be 23.6 and the normal force has to be 588.6. Okay, so that's that question. Before I go on, I want to make a note here. This question had constant angular velocity. And it's important to note because there are a lot of similar looking questions to this. So this was a question about what kind of forces are on an object that's going in a circle and what's responsible for those forces. It's kind of tricky if all you do is remember your half-remembered high school physics. In this case, the force that's pushing the person in a circle is static friction, okay? Which is weird because the person's moving. Static friction is a force between two surfaces that aren't moving relative to one another. So your disc is going in a circle and your shoes are on the disc staying in place. So it's static friction doing that. But it's still a little bit confusing. So that's what this particular question was asking. What's the relationship between rotational motion in terms of angular velocity and rotational motion of an object moving in a circle? And what are the forces that you need to go in a circle? And I'm emphasizing this because there's a related question that we have since introduced into the course, which is conservation of angular momentum. The deal here is that we're talking about a carnival worker on a merry-go-round, and we specify the period, okay? So the deal is that in a merry-go-round, there is an engine. There's a motor that's pushing everything in a circle, that's maintaining a constant speed, that's regulating how fast the thing is going around. So this system is not isolated. If the system is isolated, the total angular momentum would be conserved. Okay? And so in these types of problems, we did this in the second last week of school. In these types of problems, I would have you calculate the initial moment of inertia and the final moment of inertia. So if you find me asking you questions about initial and final moments of inertia, you might be in a situation where total momentum is conserved. And in that case, the angular momentum wouldn't be constant. Instead, the angular velocity wouldn't be constant. If the moment of inertia changes and the system is isolated, then if the moment of inertia changes, the angular velocity is going to change. Okay? So how can you tell the difference in terms of doing a question? It has to do with the clues. Often I won't spell it. Sometimes I will, but often I won't spell out this thing is isolated. Instead, here, let's do a comparison. Just get rid of all this U. Okay. Oops. How can you tell? Often I'm not going to spell out use angular momentum to figure out what the final angular velocity is. You're supposed to know. But these two situations, these two types of questions look fairly similar. So there's a couple clues that you can look for when you're doing the problem. When you're doing a rotational motion question, it will often be in a context where a motor is implied. A motor or an engine or something turning the thing, some control over the rotation. So in this case, it's a carnival. This is a machine, a ride that people ride on. In angular momentum questions, on the other hand, we will say things like, we'll talk about bearings or isolated. If the system is isolated, we're going to emphasize that it's isolated. Or maybe it's in space. In space. Free to rotate. These are the types of words you're looking for. So if that's the case, then it's not coupled to the ground. There's no control over how fast it's spinning. And in those cases, the total momentum is going to be conserved. Total angular momentum. There's another couple tells. One of these is in angular momentum questions, because when we're asking you questions, we'll be kind of leading you through the ideas. Angular momentum questions, there's often an emphasis on calculating the moment of inertia, the rotational inertia. And in this case, you won't see the same emphasis. So in this case, you didn't hear me ask about mass distribution or anything like that. Whereas in those, I might say, okay, first, I'm going to break this problem down so I can see whatever we can do. Step one, I want you to calculate I for me. Okay, so that's what to look for. It's important that you can tell the difference, because both of these things, both types of questions have relevant analysis that I want you to be able to do. So that's how to tell the difference. So in one of these, there's a constant angular velocity. In the other, the angular velocity might change. So just just keep an eye out for it. I don't want you to be confused. If all else fails, you can raise your hand and ask us. We're going to be around doing the test. So if there's any confusion about whether or not the thing rotates, you can ask us about this kind of stuff. Okay? All right. Atwood machine. With the brick sliding across the table attached to another brick with a wire that hangs over the edge. The table and the pulley are sliding on the track. Coefficient of kinetic friction between the table and brick. The table brick has mass 2 kilograms and 1.5 kilograms for the other one. Let's determine if the system is speeding up or slowing down. Okay. You know, I saw a lot of people who just knew the equation for this. And depending on how you input... I don't know how to emphasize this enough. This particular course is about learning how to think like a physicist, learning how to break down physical systems. It's not about using the right equation at the right time. So often people on this, they had some equation written down, and it was the wrong equation because this particular question is subtler than that, and people would just write down the answer using the equation, and they wouldn't know why the marker gave them essentially pity marks. The whole question's out of like, I don't know, 10 or something, and they would get like 1 or 2 out of 10, and they'd say, but look at the answers I gave, and it's just like, no. When you're doing these questions, more often than not, when I give you the question, I'm going to break down the question into simpler parts, in part because I want to see the methods that you're using to analyze them, and I want to see that you're reproducing the method of analysis that I've been trying to teach you in class. And so if you're not doing that, you know, if you have another good and workable method that's true, fine. Just make sure you're answering the questions. If, on the other hand, you're just looking on your equation sheet, which equation do we use in this context, you're doomed, dude. All right. Expression for the components acceleration vectors in terms of the 2 bricks. Now I'm breaking this down very slowly for you. All I need to know is I want you to represent as vectors what the accelerations is. Specifically, I want you to recognize that the acceleration of the 2 objects are related and refer to those vectors in terms of knowns and unknowns in terms of these coordinates given. Okay? So the easiest way to do that is to say, okay, this velocity has to match this velocity. So let's suppose this guy's accelerating to the right. I don't know which direction it is accelerating, but if it accelerates to the right with this one, then this one has to accelerate down with the same amount of acceleration. Acceleration vector A, x direction, acceleration vector A in the y direction. You know that it's accelerating along the table, so the y component is going to be 0. I don't know how big that acceleration is, so I'm going to just give it a variable name. But I'm going to guess it's to the right. Now acceleration B in the x direction. Acceleration B in the y direction. I don't know how strong the acceleration is, but I do know which direction. I know it's not in the x direction, and then it must only be in the y direction. And if this one is moving to the right, then this one is moving downwards. Right? That, in terms of this xy axis, downwards is a minus. I'm using the same letter. It's not much of a step, but this element to the analysis is critical. It doesn't look like very much, but what I'm saying is, 1, I know which direction they're accelerating. I know which plane which axis is accelerating along. And 2, I know that those accelerations are related. This problem can't be cracked without acknowledging those 2 aspects to it. Write an expression for the components of the total force. Okay, so essentially I'm just going to multiply each of these by the masses. So F net A in the x direction, F net A in the y direction. So the A has mass 2 kilograms. So this is going to be 2 times A, and this is 0. F net B in the x direction, F net B in the y direction. This is minus 1.5 A. You dig it? Free body diagrams. A has a couple forces on it. There's friction, there's a normal force, there's gravity, and there's tension. B has a bunch of different forces on it. There's tension, there's gravity. Put it all together. What we mean by this is list the components that you know and don't know of each of the forces, and then add them up to get these values. That information in combination should give you an algebraic system that you can solve. So this one, I don't know how big the friction for. Okay, so let's start. The weight is in the y direction, and it's minus 9.81 times 2. So it's minus 19.6. I don't know what the normal force is in the y direction, so I'll call it little n. The friction force, it's in the x direction. It's in the minus x direction specifically. I don't know how big it is, but I do know that it's related to that variable there. Let's see, so it's 0.8. And the tension force, I don't know how big that is, but I do know, wait, hold on. Minus. I do know that the tension's in the positive x direction. Now these ones, there's tension, weight for B in the y direction is 1.5 times 9.81. minus 14.7, and tension is in the y direction, and I don't know its value, but it's upward and has the same magnitude. And now I'm going to add these all together. So you can do it like this. You don't have to write each and every term. Like I don't necessarily need to write x is equal to 0. You can if you want. If you want to be sure that you get full marks because you're going to mess up later, go ahead and do that. But it's not entirely necessary. Okay, so now I'm going to add them up to be these. So in the x direction, t minus 0.8 times little n is equal to 2 times a. And in the y direction, they add up to 0. So minus 19.6 plus little n, and there aren't any other n terms. Now these ones. It's 0 plus 0 is 0, and minus 14.7 plus t is equal to minus 1.5a. And now we solve things algebraically. So this step is me putting all of this information together with this stuff. That's what I mean when I say put it together. Now I just need to solve, say for n, that's equal to 19.6. And then this equation here becomes t 19.6 times 0.8. 19.6 times 0.8 minus 15.7 is equal to 2a. And this one is t minus 14.7 is equal to minus 1.5a. And so we can solve these algebraically. Why don't I do it? Let's subtract them. So this is 15.7 minus 14.7 minus 15.7. So that's minus 1 is equal to 3.5a. So a is equal to minus 0.286. Hey, why is it negative? It's negative because the thing is moving to the right, And a negative acceleration means that the acceleration vector actually points in this way direction, so it's slowing down. All right. Okay. Before I go on, I've got a couple questions on the thing. First question. Hey, I'm wondering how the group test works. The group test works going to work like this. You're going to get a test. It's going to have some multiple choice on it. It's going to have some long answers on it. And it's going to be maybe twice as long as the midterm. You're going to get 2 hours to do it, which is twice the time you get for the midterm. And then after that, we're going to take a couple minutes. You're going to sign your individual test and hand that in. And then you're going to break up into groups of 3. If you don't have any friends in the class or anybody you want to work with, then 3 or 4. Then what's going to happen is we're going to just group those remaining people up ourselves. We're going to say, hey, if you don't have a partner, raise your hand, and we go, okay, you're with them, and you're with them, and we'll just group you up with some randos. And then your group gets one test booklet to do all of its writing in. You're not allowed to break it up into pieces. You're not allowed to tear it up, so that only one person can write in it at a time. And then your group pretty much has to agree on what the answers are. And then so you're going to have to discuss what you remember and how you did each question with your group. And then afterwards, your final grade is going to be, your final exam grade will be 85% your solo test and 15% your group test, with the additional thing where if your group test was lower than your individual test, then we're just going to count your individual test. So the group test can't bring your grade down. Next question. Will the style of the final be more like our midtimes or more like the practice final you posted? Maybe a little bit more like the practice final I posted. You have to keep in mind, though, that with these practice finals, every year we change textbooks, and every year we've been changing textbooks. And so every year we teach this, the emphasis and the specific lessons that we teach change. So last year's final was written, I think it was Dr. Hopkinson and I were teaching the class together. I can't quite remember last year. I think it might have been. Anyway, so it's usually a collaboration between Dr. Hopkinson and I. And so pretty much half the questions will sound like my questions and half the questions will sound like the types of questions he asks. So there's that aspect to it. It won't just be questions that I've personally written. Some of those questions are written by other people, so they have slightly different phrasings. So it might be a little bit more like last year's exam than not. But on the other hand, last year's exam we covered different material. The emphasis is different, and so the specific questions that we'll ask from last year's test might seem a little bit alien to you because you haven't, the overlap between the course isn't 100%. It's from year to year it's about 85% overlap. So like I said, some of the questions you'll look at it and be like, how do I even start? Whereas when we did it, the class that year, we would have spent an hour in class going over those specific types of questions. That said, if one of them had to write your test, they'd be even more skunked, because, yeah. All right, so I'm going to get on with the next question. That's it for this test. Look at all this scrap. Oh, you should note that we're going to give you the moments of inertia table in your textbook. Okay, so that was the pyramid midterm. Let's do the bunny one. Okay. So let's go. Is it possible to invent a system, this is multiple choice, where the object moves along a circular path at a constant speed using the static friction force? Yes, of course you can. We just saw one. That disk question from the other test. It's definitely like that. Yeah, you can do it. It might get kind of dicey in some circumstances, but you can pretty much use any force to cause something to go in a circle. What about drag? Can you use drag force to make something go in a circle? I mean, sure. Imagine you've got a ball and you want the ball to go in a circle on the table. So what you do is you buy a blow dryer. And you blow air on it in a way that makes it go in a circle. Yeah, you can use any force. Some forces are easier to use to make things go in a circle than others, but pretty much the sky's the limit. I don't know of any force that you can't use to make something go in a circle. Just some forces require a lot more engineering than others. Next, we're taught that an object moving with constant velocity, no acceleration, requires all the forces on the object to balance out. It's true. But you know, when watching the Olympic swimming competition, the very fast swimmers have huge muscles. Oh man, look at this beefy swimmer guy. He is so beefy. They tend not to have huge biceps. Big calves though. Okay. Why? So the first thing is, these questions are kind of tricky to do, and also this particular question was, I don't know, I don't think it was my proudest written question. So I'm going to draw myself next to one of these swimmers. You will note that I have a gut. I've got big legs too. Yeah, look at those giant legs. And I'm wearing a watch. Okay, so the way to do these questions is to kind of look to see, think of them as 4 true or false questions. You want to go through them and look for false statements or true statements, because essentially we're looking for whether you can tell, yeah, you're just looking for false statements in it. So consider each individually. When moving through the water, you encounter the drag force. That's true. Which is the same on a swimmer at all speeds. That's not a true statement, because the drag force, what is it? It's rho, there's a 4, there's an a, v squared, right? It depends on the speed, quite dramatically. So this statement is not true. The faster the swimmer goes, the more drag force they feel. When moving through the water, you encounter drag force, which is much stronger at high speeds. That's true. But a swimmer needs to push much harder to maintain a higher constant velocity moving through the water. Yeah, they would, right? Because if they're moving at constant speed, then there's going to be a drag force pushing them back. And the faster they're going, the bigger this drag force is. And so their swimming forces, them pushing off the water, needs to be as big as that drag force. And so the bigger their speed is, the bigger the drag force is, and the harder they have to push across the water. So that statement's true. A swimmer's cross-sectional area is smaller if they are skinny, so they try to be as narrow as possible. So some of you were like, hey, that's wide. And I'm like, hey, it's not as wide as that. That's what we're talking about. Also, kind of narrow here. Not very narrow here. Athletes tend to build bodies that essentially do well in their circumstance. In sumo wrestling, you want, you know, the bigger the gut. It's kind of helpful. You have more mass to push people over with. In swimming, you want a really small cross-sectional area. So, yeah, this one is also true. Swimmers know that they'll be on television without flattering clothes on. Since they are vain, they work out a lot. This is a false question, but the marker didn't mark it because he thought it was kind of unfair. Because all the swimmers I know are not vain. They are very diligent people. But, you know, so this question, the marker threw it out. So these are the answers. Compact disc is still... Oh, there's another question. Hey, coach, just wondering, how would the group test work for people that are writing with the DRC and have separate workspace and extended time? That's a great question, Derek. The deal is, if you're working with the DRC, you have an earlier start time. I think you start at 7 something. The DRC should have contacted you about it. And the way it works is you get extended time. So let's suppose a person has 1.5 times at the DRC. They get 1.5 times to write the 2-hour portion of the test, the solo portion. And then at exactly, I think it's going to be 11 a.m., I think 2 hours into the gym test, they're going to take the people at the DRC room and bring them down to the gymnasium to write your group test with the rest. So yeah, you'll be writing the group test with the rest of the class. All right, question. A contact disk is still, but then when I turn on the machine, it begins spinning at a frequency 600 revolutions per minute. What's the compact disk's angular velocity at the end, when it's sped up, in other words? Angular velocity is 600, okay, revolutions, that's cycles, per minute. We want to turn this into radians per second. So I want the top one, instead of revolutions, to say radians. There's 2 pi radians every 1 revolution. And I want the minutes to say seconds. 1 minute has 60 seconds in it. So this is what I use to calculate. 600 times 2 times pi, divided by 60. 62.8 radians per second. Like I said before, you could also write 1 over s. The radians I'm writing here is just to kind of help you. Okay, somebody else just came on and asked, I know somebody already asked this, but I was not watching when you answered. Is the final more similar to our midterms or practice final posted? The answer is a mix. Every year the contents of the test change, or every year the contents of the course change slightly. There's a pretty large overlap between the contents of the course, but the nitty-gritty, what types of questions we ask, differ. And so last year's exam will be a little bit alien to you for that reason. The emphasis and the types of detailed questions we'll ask in that context are different than this year's. We did rotational motion a lot earlier this year. On the other hand, the midterms didn't have any John Hopkinson type questions. John Hopkinson's methods for asking questions are different than mine. He asks more intuitive, more reasoning questions, whereas I often just say, hey, do this weird calculation. So the long and the short of it is, last year's final exam was written by both of us, just like this year's final exam is. And so last year's final exam has the same mix of John Hopkinson to my questions as this year's final exam will. Last question. Just wondering if the final has emphasis on the new material rather than the material covered in the midterms. Yeah, there's emphasis is an interesting word. These midterms, we had the midterm quite late, and so there's going to be a big overlap between them, between the material. So it's not going to be 80% energy and momentum, 20% not. But the energy and momentum stuff will be, I don't know, maybe 20 to 30% of the midterm, and the rest will be older stuff. I think that's probably about the breakdown. All right, let's get back to the questions. Speeding up requires this much time. Find the angular acceleration. Okay, so we're going to assume constant angular acceleration. Final angular velocity, initial angular velocity, alpha, delta t. So I know the final is 62.8. The initial angular velocity is 0. I don't know alpha. Delta t is 0.4. So alpha has to be 62.8 divided by 0.4. 157 radians per second squared. Write the equation of motion for angular position of a point of the disk, starting with theta 0 when the disk begins changing speeds. So that this means set t equals 0. Alright, so plus omega initial times t plus alpha over 2t squared. So the angular position is going to be the initial angular position plus the initial angular velocity times time plus the angular acceleration, t squared. How many rotations does the disk undergo in the time it takes for the speed to change? Okay, so it took 4 seconds. So what's our final theta after 0.4 seconds? 157 times 0.4 times 0.4 divided by 2. 12.56. This is in radians. We're asking about rotations, so it's going to be 156 radians. I want to write it in rotations. There's one rotation every 2 pi radians, so I'm going to divide this by 2 pi. And it's 2 rotations. Carnival worker, 50 kilogram, merry-go-round question. Okay, so I'm going to emphasize, if you're coming in late and watching this, we did a question just like this. There's issues with these particular questions. Actually, before I go on, when we did this question, we didn't have any idea about torque and any idea about moment of inertia. And now we do. So you may or may not get this specific type of question, but on the exam it's possible that this particular analysis is the end point of an analysis involving torque and moment of inertia, right? So we might start, on the final exam, we might start a question that goes like this. Here's a disk of radius, you know, r is equal to 0.1 meters, and mass 3 kilograms, and it feels torque tau is equal to 300 newton meters, right? And then so this question might start by us describing what the disk is and the torque on it, okay? In this case, you'd have to use the formula for the moment of inertia of the disk to find the moment of inertia of the disk, set some number. And then given this torque, you'd find the angular acceleration, which is tau over I. Calculate that number, and then use that number to essentially do a kinematics question like this. So this type of kinematics question is just the tip of the iceberg in terms of more complicated mechanics questions we might ask you. What brought that up is there's a similar issue with these questions here. We can now, in this question specifically, the angular velocity is a constant because it is understood that the thing is moving with a constant period. We might extend this type of question into questions involving calculate the moment of inertia for the system, calculate the angular momentum, and then in a system like this, it's possible, depending on the description, for not just the moment of inertia to change, but depending on the situation, the angular momentum would stay the same, and we would talk about we might talk about, well, not just, I mean, the torque is the rate of change of the angular momentum. So I guess we could say, hey, if it took them for this long to do that, how much torque was there on the disk? Probably not. Long story short, this particular question has gotten a lot more complicated. In this situation, the angular velocity is constant on this question, on this test, but that won't necessarily be the case on the final exam. If there's any confusion, if you want me to elaborate during the exam, you can just raise your hand and say, hey, is this disk isolated? If you say, hey, is this disk have total constant angular momentum, is it constant? I won't be able to answer that. But if you ask about the system, is the system isolated from the environment? I will, and I'll say yes, it is, or no, it's not, and that'll give you a clue as to whether or not the angular velocity is constant or not. Okay, so the angular velocity is just the change in angular position divided by the time it takes. So it takes 25 seconds to go around the circle. 2 pi divided by 25. 0.251 radians per second. It's the same in both locations. That said, the speed they're traveling in both isn't the same. R omega, R omega. The angular velocity is going to be the same because it's on a machine that's turning at a constant rate. It would be super weird. Okay, hold on. There's some other questions. I'm going to finish this question, then I'll answer the other ones. Alright, so the first radius is 3 meters, so it's going to be 3 times 0.251. So it's 0.753 meters per second. And the second radius is 5, so it's going to be 5 times 0.251. Okay, so those are the speeds. At which location is the acceleration larger? You can do the calculation if you want. The acceleration is going to be, okay, so acceleration is v squared over r, right? Alternatively put, omega squared times r. So you can use proportional reasoning to argue that wider radius means bigger accelerations. Okay, when she's at the 5-meter location, determine her acceleration and net force on her. Obviously, if I give you a little axis like this, it means use these axes to describe these vectors. The acceleration vector in the y direction is 0. The acceleration in the x direction is v squared over r. So that's 1.255 all squared divided by 5. .315. Okay, so before I go any further, is this supposed to be a positive or a negative number? I know the acceleration points inwards, and that's in the positive, increasing x direction, so it's probably going to be a positive number. To find the net force, I'm going to multiply these by her mass, which is 50. So that's 0 times 50 is 0. 0.315 times 50 is 15.8 newtons. Draw a free body diagram. It's going to be gravity. It's going to be the normal force. Static friction. It's going to push her towards the middle. Let's write these out in terms of components. That's 0. It's going to be in the minus x direction, 50 times 9.81 minus 491 newtons. Normal force in the x direction is 0. Normal force in the y direction is, I don't know, but it's some value. Friction in the x direction, it's in the positive x direction, right? It's pointing towards the middle, so I'll call that plus little f. And then friction in the y direction is 0. So now I'm going to put them all together and add them up to equal these. First the y directions. Minus 491 plus n plus 0. And then the y one, the x one. 0 plus 0 plus little f. So little force is equal to 15.8, and the normal force is 491. Okay, before we go on, some people might be like, hey, what about, this is a friction force, what about all that mu stuff? Well, this is a static friction force. Static friction is as big as it needs to be up to some maximum. We didn't specify what the coefficient of friction is, so we don't know what the maximum is. But we know, since the person is moving in a circle, that there has to be this much friction force on it. There's no way to tell if this is beyond the maximum, but it's probably not. Okay, Atwood machine. Alright, before we go on, let's answer these questions. Okay, first question. I heard someone say it's 30% of the first midterm material, 30% of the second, and 40% of the new material. Maybe kind of. There's a lot of overlap in the new material with the older stuff. So, you know, there might be a question where it's just like, hey, there's an object, it feels forces, and these forces do work. So first, calculate the forces. That's all stuff from the first midterm, right? First and second midterms. And then after you calculate force, it might say, calculate how much work gets done, which means you do the dot product vector multiplication calculation. You find the angle. So there's a lot of overlap between the two. Most of the momentum stuff, there's really not much to these momentum calculations or these energy calculations that we haven't seen already. So it might be 40% of the new material, but even in that, a good chunk of the new material, quote unquote, is going to cover old material. Last question. Will you be doing a video on the practice final? I won't. I don't have time. My finals need to be done, printed off today, and then, yeah. And so we're still working on the final questions, and yeah, I don't have time to do that. I'm sorry. But yeah, John Hopkinson made solutions. I haven't looked at them, but I uploaded them. You're adults. You can figure it out. I set up an Atwood machine with a brick sliding across the table, attached to another brick with a wire that hangs over the edge table. Blah. The table on the brick is initially sliding to the right, and the coefficient of kinetic friction between this table is 0.2. The table brick is a mass of 3. Okay. Sherry Marie said our exam is at 1, right? Sherry Marie, which class are you in? Physics 112's exam is at 9 a.m. Physics 111's class is at 1 o'clock p.m. So Sherry, if you are in Physics 112, then double check your times. If you're in Physics 111, then your statement is correct. Also, if you're in 111, their second midterm was a lot earlier in the term than 112's was. So yeah, so the final will cover more new material. Okay, so like I said in the last one, in this case, what you don't want to be doing in these questions is just relying on equations in your equation sheets. Read the question, try to figure out what I'm asking you. The steps I'm asking you to do correspond to things we did in class, methods I've been trying to teach you in class. That's what I'm testing you on. When you're out there in the real world trying to figure out how antelopes jump so high, there's a lot more moving parts than a stupid Atwood machine. But the methods I'm trying to teach you will work just as well for the jumping antelope as it does from the Atwood machine. Which is to say, what do you know about the acceleration? Write the things you know, write the things you don't. What does that tell you about the net force? Write the things you know, write the things you don't know. What forces do you see acting on it? Write the things you know, write the things you don't know. Put it all together as individual steps. If you just look up on your equation sheet and pull out an equation, and you're like, this one looks right, chances are it won't be right. And if you just write the answer based on that equation from your equation sheet, if you're not answering the questions I'm asking you, you don't get any marks. That's the long and the short of test-taking strategies. In university, answer the questions. There's 400 people today writing this test. Just answer the questions we're asking you specifically, and everybody will have a good time. I know that you feel like you know more physics than we're giving you marks for. Answer the questions we're asking you. We want to give you part marks, but there's hundreds and hundreds of you, so we come up with these marking schemes. Just answer the question we're asking you. I beg you. That's all I want you to do in this life. Write an expression for the accelerations. Okay, so there's an element of assumption here, which is that we have to assume that the brick's either going to the left or right. Let's assume that it's going this way. that corresponds to this one accelerating upwards. Why did I say that way? Well, I know I know it has to be left. I know that this one has to be left right, and I know this one has to be up down. And I know that these two directions have to be related, so this one can't accelerate down if this one is accelerating to the left. But that's really all I know. So it's a guess. And it doesn't have to be a right one, because if I do it systematically, algebra will cover for any misassumptions I make. So the acceleration in the A direction, acceleration X direction, Y direction. All right. So this one's, A is only accelerating in the X direction. So let's see. This one I've drawn is in the minus X direction, so I'll call it minus A. It's not accelerating in the Y direction. So that's 0. B isn't accelerating in the X direction, and according to this drawing, it's accelerating up, so that's plus A. Net force. So the first one's mass is 3 and the other one's 2. So it's minus 3A. It's A. Alright, so this is 0. F net. Y direction, that's plus 2, right? Yeah. All right, free body diagrams. A is going to have a normal force. It's going to have a weight. It's going to have a tension force. And it's going to have a friction force. B is going to have a tension force. And it's going to have a weight. Okay, now I need to put this all together. What was it, 3 kilograms? So this is 9.81 times 3, so this is going to be minus 29.4. Normal force is also only in the y direction, so I'll call it plus little n. Tension force is only in the x direction. I don't know how big it is, so I'll call it plus t. Friction force. I don't know how big it is, but I do know that it's related to that variable. So the coefficient of friction here is 0.2. So it's minus 0.2 times n. Hello. Hello? Hi. Oh yeah. Uh-huh. Yeah. Okay, that was a phone. Alright, so the weight for object B, it's 2 kilograms, right? Yeah. 2 times 9.81, so it's going to be minus 19.6 newtons. The tension force, I don't know how big that is, but I do know it's in the y direction, plus t. I'm using the same variable for both of these. Now I put it all together. Let's put all the x terms together. T minus 0.2 times n is equal to minus 3a. And the y terms, they add up to 0, so there's minus 92.4 plus little n. And then in this case, there's only, well, the x terms are all 0. And the y terms are minus 19.6 plus t is equal to 2a. And now I solve these algebraically. So this is what I mean when I say put it all together. So n is equal to 92.4, and so that other equation becomes t minus 18.5 is equal to minus 3a. This equation here is minus 19.6 plus t is equal to 2a. I solve it. Let me use subtraction. So I'll make this one plus, and this one minus, and this one plus. No, that one's minus. And I'll combine them. 19.6 minus 18.5 is 1.1 is equal to minus 5a is equal to 1.1 divided by 5 minus 0.22 meters per second squared. Hey, it's a negative number. What does that mean? Well, hold on. We assumed that the acceleration was that away. Since the variable here is negative, the acceleration for a in the x direction is going to be minus 0.22. So it's going to be 0.22. So it'll accelerate forward, so it's going to speed up. Okay? Well, that's it for this online office hours. Keep in mind that this particular online office video is for Physics 112, biophysics. If you're in Physics 111, which is physics for quantitative science students, have a fun watch, I guess, but you need to know something, which is that our test in Physics 112 will be a 2-part exam, and our test in Physics 111 will not be. Our test in Physics 112 is partially written by John Hopkinson. Our Physics 111 class is partially written by Jake. So, yeah, pay attention to that. All right, I'm going offline. Time to get back to work. Have a nice day. Good luck studying.